Hi everybody, my name is Rogerio Bonatti. I'm a senior researcher at Microsoft, and I'm here with my colleague Shuang.
Hi everyone, I'm Shuang Ma, and I'm also a senior researcher from Autonomous System Research Team from Microsoft. And we are happy to introduce our work LATTE this afternoon. So my colleagues, Rogerio will introduce more about that.
Yeah, so it's a pleasure to be here at the NeurIPS booth at Microsoft. And here we're going to talk about our work called LATTE, the Language Trajectory Transformer. So this is a paper that we're going to present at a workshop on Saturday. In case you're interested, it's the Foundational Models for Robotics workshop. And this is a work that I want to say was done in a collaboration with a fantastic team, both at Microsoft and the Technical University of Munich. So the main idea behind this work is that we are investigating how we can create more effective interfaces between humans collaborating with machines, collaborating with robots. And in fact, there are many types of interfaces that we can use when we think about this interaction between humans and machines. Just to cite a few of them, we have interfaces that can depend on natural language, so that's basically a human speech. We can have traditional mouse and keyboard interfaces. We can have computer programs that users type and code in order to produce behaviors in the robot. We can use sometimes drawing, so you can potentially draw use a pen on a tablet and draw a trajectory for your robot. We can use kinesthetic teaching, where you physically grab your robot and show it how the motion should be done. Or we can use touch screens, I could spend the whole day listing different interfaces between humans and machines. But the big issue here is that it's hard to have an interface that is flexible enough, that allows the user to do different types of commands, that is easy to train the user to use, and that is also precise in its motions. Usually we have to choose one, or sometimes at best two of these requirements and just go with it. But then the goal in this project is we're trying to achieve all three at the same time for an interface between a human and a robot. And specifically, we're focusing a lot on a language interface between humans and machines, because language is in fact the most natural way that we have to communicate with each other, and naturally we want to use the same type of communication structure with a robot. But the big issue is that classical language interfaces between humans and machines are very complicated. Just to give you an example, classically how this is done is we process the language tokens into a semantic representation. Then we have to ground this into basically cost functions that are going to be used by a traditional motion planner by this robot, and then have the robot execute those plans. But almost every single step of this framework is very fragile and is prone to errors and issues during its execution. What we want to do with this paper, with LATTE, is to follow some of the recent advancements we've seen in natural language processing and try to use them for robotic systems as well. So in the field of traditional natural language processing, we've seen a shift from traditional architectures that deal a lot with language parsing. And we have seen the shift towards newer approaches that use basically large language models to process this data in an end-to-end fashion. But some of the requirements for this is we need a lot of data to train these models. We need a lot of compute power, and also we need quite large models. And we're trying to do the same thing for this aspect of human-robot interaction. So go from these very kind of classical interfaces towards a neural model that is able to do this interaction end-to-end. But we have a lot of questions about how do we actually get there. So to be a little more clear on what we've done in this paper is we've chosen this natural language interface to modify a trajectory for a robot so that it can obey language commands given by the user. So just to give one particular example, a user can tell the robot to stay away from some glasses, and we modify this trajectory so that we obey both the geometrical and the semantic constraints from the user. To give you an example of what this system is capable of doing, let's take the scenario of a robot barista that is serving a beverage to some grad students that are working all night on a paper. And initially the robot collides with a tower of crystal glasses that are on the table. So a user may send a command such as, robot, stay further away from these glasses. And what we want what we want the robot to do is to execute this maneuver and be able to pour the wine without causing any accidents on the way. I know there are some mathematical definitions. I'll try to be very quick and take this lightly. But basically, we have a trajectory that is defined in R4. So we have x, y, z positions and velocities that parameterize this trajectory. We also have a bunch of objects in the scene. We can have many types of objects, and each one has a particular position and an image label. So basically, we assume that we have a camera, either at the robot or maybe a third-party camera that is overlooking the scene, and we can take images of each one of the objects. We also assume I have a language input from the user, that is the language command. And what we're trying to do mathematically in terms of machine learning is to learn a function that maps the language command, the object positions, and this original trajectory for the robot, and maps this towards a new trajectory that obeys the geometrical and semantic constraints. So this is a snapshot of the system that we have. I know there are quite a few blocks over here, so over the next few slides I'll be going over the details of each one of these blocks. But basically we have on the far left the natural language inputs and the inputs in terms of object images and object poses, and the trajectory for the robot. We process a lot of these image and vision inputs into a few pre-trained models from BERT and CLIP features. And we use a TransformEr encoder to find features, geometrical features from the original trajectory for this robot. Then we use a TransformEr decoder architecture to output a modified trajectory that the robot should execute. We do have a few safety checks, so we don't simply execute whatever our machine learning model outputted over here, but we do a few safety checks in terms of constraint satisfaction. We check if we're colliding with any obstacle. And finally, we use inverse kinematics modules to be able to follow these trajectories using any type of robot. And we've done this with flying robots, manipulators, and also a few hexapod robots that look like spiders. So you'll see a few videos later. I do want to emphasize a few challenges that we find here when we're dealing with robotics data in comparison with pure language models. Whenever we're only dealing with language, we find that we have a single modality. So we have usually text as an input and also text as an output of these models. However, when we're dealing with robotics, we find that we usually deal with multiple modalities of data. For example, we can be dealing with images, with text, geometrical information. So we have a much higher dimensional problem at our hands. We also deal with actions, because the robot is interacting with the environment, and its actions cause changes in the environment around it. So so we also have to take into account all these multiple modalities of data, which are effectively much harder to collect in comparison with just downloading a data set from the web or just scraping images or text from the web. And specifically on how we get these labels for language labels for robotics tasks, there are many types of methods we can use to generate these types of labels. One way is to actually have user-generated label data labels. So you can ask the robot to do something, and basically you have a user that will label for each language command. A user will actually show the robot what exactly should be done. And even though this is very high quality data, it's really not generalizable. It's not scalable, because you need a proportional number of users if you want to get more data out of the system. A second strategy we can also use is a posteriori labeling, where for example, if you just have a bunch of videos that were downloaded from the web or scraped from the web, you can ask users to label those videos afterwards, after they were collected. And this method is slightly more scalable in the sense of you don't need to run large-scale user studies, but still you need a proportional number of users to label the data a posteriori. But the method we chose for this paper was to use procedural generation, because we didn't want to be bottlenecked by not being able to generate enough labels to train our system, to train these transformer models. So what we did was we are procedurally generating a bunch of sentences, and we use a motion planning system to generate the deltas in the trajectory positions, so that we know how much the trajectory should be shifted afterwards. And one key idea in this paper is that even though we are using procedural generation, we are leveraging knowledge from existing large language models so that the data that we generate, even though it's low in terms of the diversity of the types of sentences that we see, we are still able to adapt to different ways of expressing the human intent using language. So to give an example, even though in the training vocabulary we only saw sentences that, for example, just tell the robot to stay away from some particular object or keep some distance from X, we are also able to generalize to a lot of unseen vocabulary, such as avoid being close to X or move away from some particular object, even though we never saw the sentences during the training procedure. So this is a big advantage of using this pre-trained large language models, because they offer us rich representations, and we are able to deal with with a lot of the vocabulary variation. To give you an idea of how we generated data procedurally for this problem, we have a couple examples. So on the left, you see we have a 3D environment where we randomly place a bunch of obstacles on the way. And for example, we're shifting the trajectory to drive much closer to a particular, to the boathouse, one of these objects. And you can see how the red trajectory, which was our original guess, is shifted towards the blue one over here that is much closer to the desired object. We also input images of these objects towards inside of our framework, so we scrape the web for a bunch of images for each one of the objects. So that's how we get away with being able to deal with both language and vision features. And on the right side, you see a different kind of trajectory modification, where we're telling the robot to go faster when it's close to some other particular object. And now I'm going to go into a few of the details of how we actually process this vision and language tokens. So we pass the language input into a distilled BERT frozen pre-trained model, and what this is going to do is it's going to extract a lot of the semantic meaning behind what the user is trying to instruct the robot to do. And on the right side, we also input images of each one of the objects in the scene, and we can use standard feature detection architectures to get an idea of what exactly we have, which types of objects we have in the scene. And the idea here is we're not only telling the robot to do something, but we're also trying to identify which objects the user is referring to. If you tell the robot to stay away from the bottle, you actually want to stay away from the bottle and not the apple in the scene. So what we do here is we pass both the language and the image modalities through a clip frozen model, and we use we compute a similarity vector between the language and the image embeddings to know which object we're referring to. So the module that I just explained is on the left side of this image, and we have to combine all this textual and visual information together with the geometrical information. As for the geometrical data, we use a TransformEr encoder architecture that encodes all the object poses and the initial trajectory for the robot into a latent vector. And then both these vectors are going to be fed into the TransformEr decoder module that outputs the final trajectory for the robot. Just going one level deeper into how this architecture works, something I want to emphasize is that this is a very, very similar architecture to how language translation is done. So imagine if you're trying to translate a sentence from English to German. We're doing a very similar procedure where basically we're trying to translate a trajectory from one space that only obeys geometrical constraints towards a new space that obeys both semantic and geometrical constraints. So we have a very similar type of architecture here. I want to show you a few videos that exemplify what this model is capable of doing. So here you can see in a kitchen setting, we are able to modify a trajectory. The original trajectory is going pretty close to the human and quite fast. And the human tells the robot to go slower if you're close to me. And our algorithm is modifying the trajectory and making it slower whenever it's close to the human. Yeah, on a second example, imagine that you have a teapot and for some reason, you're trying to code on your laptop below the teapot that is being moved by the robot. You're able to tell the robot to keep a bigger distance from your computer, and the robot is able to execute this command as well. And this is actually a 3D motion, so the teapot is coming towards the camera position, away from the human. We also have additional experiments where we tested different types of robots being driven by the system. So we have simulated experiments with a drone. So you can fly slower, close to the table, or stay away from some particular object. And we also had some experiments with a few crazy robots like this hexapod. So you're trying to stay further away from the computer. And this just shows that the inverse kinematics module, even though we're using a single model to train the transformer for the trajectory output, we can use multiple inverse kinematics modules to follow these trajectories. Yeah, so these are just a few pictures that show the different kinds of examples that were in the video. Maybe a few other scenarios as well. Just maybe a minor technical detail. We also played around with putting a few other knobs for the user to modify. So the user is also able to modify the intensity of these changes. So we can change the how far away from basically the intensity of this change in terms of the amplitude of the motion as well. And also to evaluate the system, we do have a lot of kind of qualitative videos showing what the system does, but we did put it through a user study to quantify how better our system is compared to other types of human-robot interfaces. So we compared our natural language interface with kinesthetic teaching, basically parameter tuning, if you're actually coding the robot to do some behavior, and trajectory drawing. And if anybody has questions later, we can go over the actual numbers, but basically we can see that for most of the categories, our system was able to act faster and be more, basically more accurate for the user. We also have a few other user studies where we compared the quality of the trajectories that were generated in comparison with a few other methods. And we also, we can go into more details later, but basically we show that our system is in fact statistically more likely to generate trajectories that are useful for the users. And just in conclusion, I want to say that by using the system, we're able to generate more natural human-robot interfaces. And we saw how we can shape these robot behaviors by using natural language commands. And we saw how these commands, the same model can be applied towards multiple robot form factors, from manipulators to drones, and also maybe walking robots. I think something interesting is that we have a model that operates in multiple domains. So we're operating in the vision, language, and geometrical domains. Which is something that we're striving in our group to be able to do, to align all these different modalities that are quite different from each other. And also, from the audience, I would love to hear if you have any ideas of other domains where these types of models could be applied. I would love to hear your thoughts. I would love for this to be a discussion. You can talk to me offline as well later on. And I would love to go beyond just navigation and think of other domains where the same ideas can be applied in decision making. So with this, I want to thank everyone for watching our talk, and I'm happy to take any questions right now or offline later.
Yeah, so if anyone has any questions, we will help to answer your questions and for further discussion.
You can ask it from here. Yeah.
Hi.
Hey, I have a question about the text encoder you use as well as the clip encoder. You said they were frozen. Is it something you've considered to fine-tune those models for the task at hand, or does it make any sense?
Sorry, I heard the first half, but I couldn't hear the second.
So you're using a text encoder, a pre-trained BERT model, as well as a clip text encoder. You said they were frozen for the training. Have you thought about fine-tuning these models for the task at hand or not?
So for the language model part, actually we use two language models. So first is it's a pre-trained BERT language model. So it's frozen during training, and the main target for the BERT model is to extract the semantic features from the language commands. And another language model we are using is CLIP. So CLIP is trained with both language and vision. So that usage is for us to extract the aligned vision and language features to help us to learn the alignment between the visual observation and the language commands. I think both of these are frozen during.
Yeah, I think the reason I would argue against fine-tuning the entire model, so I argue for it to be frozen and remain frozen, because since we are doing a procedural generation of the data to train the TransformEr decoder that deals with the geometry, I would say that we don't want to bias the language, this language model, to only work with a restricted set of vocabulary that we have in the procedural generation. So I would argue that it should remain frozen because we want it to be able to work with synonyms of the data, of the language data.
Another thing to use the pre-trained language model is it can help us to cope with some out-of distribution scenario. As Rogerio just showed some cases that help us to cope with out-of-world, out-of-vocabulary cases. So I think this is also the usage of this pre-trained language model help us with this thing. Thank you.
Yeah. All right, I think those are all the questions, and thank you so much for watching.
Thank you, everyone.